Welcome back, guys. So, yesterday we were trying to debug why we are not able to actually write to the Virtio registers, and whenever we write to it, we didn't see anything, and it turns out that Virtio just maps all its devices, but without a backend. Only if a device actually has a backend, we will be able to write to it. And we, as a driver, is supposed to go into all those addresses and check if a device is registered or not, and then use it. So this is what we figured yesterday, and to give a high level overview of what exactly we are doing is that we are still trying to write a file system for our own kernel, and the file system layer needs a VFS, and we also need a block layer that is going to abstract away all those operations that needs to be done by the drivers, and only give a block read and block write to the upper level VFS. And this is how we started this whole thing, and now we are actually in the block layer, and we are writing the driver for Virtio, and we did a lot of stuff and we figured out stuff. And currently, as I mentioned, we are trying to we'll have to go through all those memory mapped addresses in the Virtio and check if there is a device backend actually registered, and then go through it. So this is currently what's happening is that we, okay, still maybe 8. So we run it. Okay, what happens? Did we change that? I don't remember changing that back. We have U32, U32, U32 here. Here we have the same fucking thing. Maybe this is what is changed. How did it change though? Did I click Control Z or something? What? No, is the error? We still have conflicting types in update status. Okay, filter it. Okay, now it should work. So yeah, let's run it. And if we run it, and you can see that during our DTD passing, we just take the first, we take the Virtio MIMO that starts at 1000 something, and we consider that as our MIMO's our block devices register. But turns out that's not the case. It's just that Virtio always registers all of its drivers, and it only gives us our starting address, and we are supposed to go through all those devices and see which device actually has a register. So we did get the starting address, that's fine. So this parsing is fine, and we got the starting address. What we have to do is that we have to go through that entire address range, and check if, because currently what I do is that from that base address I'm checking if the version is 2, which is because there will be multiple devices and every device will have a version, which is the Virtio version, and device features and device ID. And as you can see, the device ID is 0. And as soon as it is 0, there's nothing else is working because I tried to write to the other registers. Even if I write to it, when I try to read from it, there's nothing there. So yeah. So, and when we actually went back and tried to look into other sources, we figured that it's simply just that we get the starting address and we are supposed to actually step into all those devices as 0x2000 as the increment. And I was thinking, why did we have this incremented value? And it's straightforward. It's just that the entire if you go here, if you just count all those fields, you will probably end up into 200 bytes, and no, 200 value in hex, and that's probably why we just have it this way. And for every device we have around 200 registers, 200 range of register, and we already have those offsets here, so we just keep on incrementing it by 200, and inside the loop we check if there is a device registered or not, and then we decide what to do. So in our case, we also still have to care about one more thing. That is, initially my assumption was that that the initial address that I have passed is the register. So my idea was to map this to a physical page. No, this is the actual physical address, and map this to a virtual page so I can use it. But now I will probably have to map every address. For that, I also have to confirm if my mapping covers how much of the range does it actually cover. So if we go to our K-main, and you can see I get this is the parsed address from our DTD. And this is we see we get the drive info, and we take the first one out of it. We print everything, but currently we only take the first one, and we add a virtual page for it, so that we can use it here. And this will be the virtual base which will be mapped to this physical. And let's check how much have we actually allocated. It is L2 entry. I think L2 entries are supposed to hold more than 200. Yeah, L2 entries are 2 MB blocks. This 2 MB page block cover 200. Cover 200 x 200 into n. N will be the value that we need to know. N is too much, so I think we don't even have to worry about it. Just that as we are starting here, it should just work fine. And we have to make sure that it is 4 bytes aligned, 4 KB aligned. I think it must be 4 KB aligned. And we have lots of n, so I think we don't have to worry about mapping it. There must be map already So what we can do is just that we write the extra loop now. So instead of considering this as the actual virtual range, we have to figure out which entry is actually the one that we want. So let's take u into 32, I equal to 0, and then we'll write the for loop, I equal to 0 less than, I think we can take up to 10, and I plus plus, and we can what we have to do is that we have to call init Virtio driver. But instead of that, let's just write an extra helper. We'll write it here. And it's almost gonna take the same thing. And let's just put it here. And it's going to check which IO driver it's going to be. And maybe we don't actually need lots of stuff. You only need an address, which is going to be a which. It does not have to be which. Okay, let's just keep it as which IO object so that rest of the things can be as it is. Inside that, we have to check 3 things. We have to check the version, device ID, and device ID. Okay, so let's do that. Is that enough? We can also check the magic number. I think magic number is fine. We'll just check the version and device ID. Or we can also check the magic number. Virtio magic value, and we read the device version and we read the device ID, and we write the condition saying magic value equal to 0x74726976, and device version should be 0x2, and device ID should be should not be equal to 0, because if it's equal to 0 then the device is not registered at all. And we can put an UART printf saying that this address is valid. And the value would be Virtio object.base address. If not, we just and we return true here, return 1 here, and return 0 here. Let's just put even 32 here. and copy this and put it here. And that should be good. Now we can just call this inside our k-main, inside our loop actually, and we just say we need a Virtio object. So what can we do about that? We'll just Virtio star Virtio equal to Virtio temp equal to, I think we can use this method, star dot Virtio base equal to, what is it? Base would be driver info. No, it should be the physical thing that we have, that is Virtio range, which should be this starting address plus, and we have this calculation of I into 0x200. I think it should be good. And we just pass the address here. Temp. Yeah, I think I should walk. And if it is true, equal to 1, then we can just break even 64 device reg equal to 0 if it is 1, and then we device reg equal to Virtio range plus I into 0x200, and we break out of the if. And if the device range is still 0, then we say uart printf no device found, and we stop here. Because as I said, there's nothing to do. If there is no device, we have to put a while loop or stop here, nothing much we can do. And then we can update this with device reg. That should be good. Let's see what happens. And we get no device found. Okay, now let's then print everything. Let's see what we get there. Maybe we are doing something wrong. Let's just print the starting address So it should be uart printf, and we have multiple things. That is current L. That should have magic with L. Magic with D, and device version with D, and ID with D. And let's just put which IO objects, and it should be which IO base, and we have device version and device ID. And yep, let's run it and see what's happening. Probably some silly mistake. Yeah, we can figure it out. So this is the one we try to read, and it has magic S2. Wait. Why is the magic value 2? Let's put L here then. Oh no, I didn't even put the device magic value. Okay. Now let's see. And let's just confirm that this is the magic number. And yes, it is 72, 69, 76, so it is fine. And it has the version 2 and ID 0. Almost every damn thing is 0. Okay. That's sad. Let's try to change one thing, which is currently we tested up to 10. Let's test up to 20. Hopefully it's even a thing. Or we might actually read an actual device and we stop before that. Even after 20 we still get the same thing. But even after 20 we still have devices to read. That's what even... Let's just put 100. I'll put 200. But that should be only 313 devices technically. That's how I read it. I don't know why am I able to keep reading the same value. Oh, so address is valid. We did find something interesting, and we are able to update the status there. Oh wow. Okay, so voice 1 2 3 4 5 6 7 8 9 10 11 12. Yes, it's too much to count. Let's just print the I. Current I value. Device found at index. Okay, let's see what happens. Ah, yes, Okay. Yeah, I also read the same thing. So because Virtio always uses the first address as the end address, so probably there is 32 devices, and 31st index is the 32nd device, and that's why it's there. Okay. So then I think we should not read like this. It should be only reading 32, but also just let's write a comment here. We are only reading up to 32 devices. And we run it, and we didn't find anything. Okay, maybe we need the 32nd one. Okay, it should be equal, because we also need the 31st, which is the 32nd device, and we found it, and it's good. And after that we were able to read the status. We were able to, yeah, we just kept updating different statuses, and ready status is this, and we got the device features. Okay, then what are we supposed to do? Let's go back to our which BLK option. Here we were trying to, yesterday we also figured out one more issue, that we also have to update the status incrementally, not overwrite it. So we did this. I think I also tried a different version, but that should have also worked. I think that would be more elegant. Maybe we can change it to that version. But overall, after that, we update all these stuff, and then we try to init the queue. And when we init the queue, what do? We currently, I think we don't need to get these two things, but it's fine. It's fine. Okay, so let's print the current max queue max size. It should be a D. It should be qmax size, and let's see. Okay, we have max size of 1024. That's fine. So we say that we want to select the what? Let's just go back to our actual thing. We have a list of stuff to do. Okay, so we selected the queue index, which is 0, and then we checked if the queue is ready or not, which is returning not 0, so that's fine. And then we read the queue max size. Okay, we read the queue max size, and we printed it. It's 1024. And then we can allocate queue pages in a continuous memory, aligning the rings, used ring to optional boundary. And the queue size should be smaller than the queue num max. Okay. We have to notify by writing queue num the size of the queue. and currently we are only going to be having it as 1, so let's just write 1 and notify the device about the alignment by writing the value in bytes to Q align. Okay, so we have to also uh, to notify it about the alignments. It's 4 KB aligned, so it's 4098, I guess. Okay, we can do that. Let's just see, we do this and we put Q align. Do we have it? No, we don't have it, so let's create that. Q num Q ready is here and yeah, oh fuck me. Align Q align should be, what the fuck, I'm reading the legacy interface, that's not good. Select the queue, we write it and we write that and device the queue num and write the physical address. See, that's the thing, this was the actual thing, we should not be doing the legacy stuff. Yeah, we don't have to write this part, let's just remove it. As soon as for the, that was legacy versions configuration. For the newer version, which is the this, we just simply have to write q index q, and after we write the queue size, we can write the physical addresses to those proper areas and finally write qx1. So that's why I have this init virtio and then I finally write it. So inside init virtio, I actually write those addresses, the upper half and the lower half. I think that is all. There's nothing much to do here. We have done everything. So I believe the queue is ready. I think we can start with the actual request now. So how do we make a request now? Just a double check because we saved it. Hope it did not fuck anything. It's all good. Now it's time to make the request. Okay. We go back. Here we initialize the queue. Now what do we do? I think now we have to start with the actual requests. There's nothing much to do, I believe, because I guess these other steps are just different features that we might try out. And as you can see, we got device IDs 2, which is a block device, so that part is also perfect. I think we might have to do these steps, but I don't know. I think let's just start with the actual requests. Let's see. See, we have Virtio block requests. Virtio BLK requests. I think that is all. We make this request because this request also has the different types, and the possible types are like read, write, and discard, flush, and zeros, and we check what sector we want and stuff like that, and we just put that request into that. I think nothing much to do because I should must. Okay, maybe we have to do one more thing, that is because currently I'm not accepting any features. I believe it's gonna hurt me back someday, because here when we read the features, why the fuck am I reading the features? No, I'm just saying that after I set it its driver, I directly say its features okay. So do we actually have to read the feature here and maybe write it into our thing? Maybe it's possible that we have to do that, because yesterday when I was reading, I believe that should be done. Let's see if we can find it somewhere. I don't know, but I'm pretty sure yesterday I read it somewhere here, because yesterday I clearly remember it like we read the features from device and we write it to driver features, because there's two different things. Because I was confused about it yesterday, because here as you can see, device has features, so we read from it, and we also have driver features, so we write it into driver features. So only then we are saying that we are accepting these features, something like that. So I believe we have to do that. I don't know how, but yesterday I remember it reading it in the stream. So I'm pretty sure it's somewhere here. As you can see, if we don't actually tell what features we accept, then maybe the queue will never be able to do anything properly, and we'll be debugging something else, which probably will end up here back again. So it's better to just finish those stuff properly. Let's just search for features. Features. Each Virtio device offers all features it understands. During device initialization, driver reads this and tells the device the subset is accepts. The only way to renegotiate is to reset the device. This allows to forward and back only if the device is enhanced with a new feature bit. Not right. Okay. Feature bits for specific device type. Maybe. But I still don't know what are these features, because in my case, device features is just this big thing. And if we convert it into hex, so these are the bits that are actually active. We have this bit active and this, and we have multiple bits here. So my question is, what does this bit relate to? What does it actually mean? Where is that documentation? Without it, how am I supposed to? Okay, let's see. Where is it? Okay, from the device which is properly as a backend device ID as 32, so it is a block try define. Now I have to accept some features from it. Only want to be able to read and write blocks. So this is the x value, and I read from device features. So what should I write into the driver features? Rich. To enable basic block writes, and you must accept write these features into driver features. Driver features select, we select the high bits that we talked about yesterday. So if we select the lower bits, that is of features of some other device, and if we select the features of higher bits, it's of different thing. So this one is enough. Okay, let's try. So what do we do? Okay, we are here, and we read the features lists first of all. So it should be uint 32 device features, and we read it. So it should be read u32, and it takes a Virtio object, and offset would be Virtio driver features, whereas device features, it's here, device features. So we read the device features. Now we have to write it back into our driver features. So we read the features from the device, write the features that we want into the driver features rich. So it should be write uint32, and it will take the Virtio objects, and we want to write into Virtio driver features, and we want to write only the 33rd bit. But how is just moving one right shifting it once, how would that become that? How will right shifting one times will make 33rd bit set. That's a stupid question, but I don't know the answer, so yeah. So it's not a stupid question. My question was correct. That was a fucking... Oh. Oh. Okay, it makes sense because as I said, so we have upper half and lower half. If we select the upper half, then we are actually writing it into 32 to 63 bit, and that means we just have to write to the second bit. If we write to the second bit, in our case it's virtually writing to 33rd, which makes sense. So we select the upper half by writing into features cell, and then we can write to 32 to 63 bits. So we can simply put 1 and we right shift it 1 times. It virtually means that we are actually writing into features, and we select feature cell and we just write 1, and then we set features as okay. Okay, makes sense. So maybe then during the read operation, do we have to select the device features upper half and then read it? So when, if this is the case, or if this is the case, so when I try to read the features from device, do I also have to set the device features cell to 1, so I'll read from the upper half? Okay, so that also makes sense. If we actually, for device, if the actual value will be 0, so if I'm reading 0, then I'm actually reading from the lower half. So I have to probably make sure I set it back here and then read it. So the entire features will be like this. So we move it to the upper half and we have the lower half, and we can have one big features. I'm reading the lower half. Features. But probably have to use cell to set the upper half and read that value too, but currently this is actually not needed because we are not using it. but just in case if we want to read it, we can read it. But as we know, we only can set the 33rd bit, and that should give us enough of what we need, that is just to read and write. We don't care about other features. Currently we only care about reading and writing, and so we just select the feature to 1 and we set the 33rd bit, and hopefully the 33rd bit actually is the one that we need, and the fucking LLM did not hallucinate. And I believe I saw it somewhere else too, it is 33rd bit, so I believe it should be fine. If not, we can come back and let's just write. We are setting 33rd bit. Is it enough for basic read and write block operation? Let's just have this question here in case in future we might need it. What else? I think it should be good now that the features are set. I think the queue is initialized. I think I'm ready to make the requests structs and that into the queue. First the process and what stuff involved, why they are involved. Okay, let's see. So send a block IO requests. We must set up the descriptor chain, which is already ready in our case because we do have the init queue, and which just make sure we are setting all those registers. And within the registers, we have 3 things. That is the Virtio descriptor table, and we have the avail table, and we have the use table, which are all set. Now we just have to set up the request header, and as you can see, we already have a structure for it, and it is here. Yeah, it has types of read and out. Did we define that anywhere? No, we did not define it. Let's just define it. We might need it. We need define which IO blk t in, and we'll get a hex code here, and we'll write also out. I think let's just start implementing these two first of all, and if we come back here and if we copy this and if we paste it here, and which in is 0 and which out is 1. Which out is 1. Maybe we can also write the flush operation so that once we write it, we flush it. Once we write it, we read it, and then we check if the value is there, and then we can again flush it and double check if the value has gone to see if the things are actually working. So let's also implement the flush operation. Flush is 4. Okay, that should be good. Now let's write a thing that is going to give out no, we don't need a helper for it. We'll just do it manually. Once the registers are done, we are here, queue is ready, and we are here. Okay, now we are gonna make a to-do is going to be prepare the request, and then we have put that into the queue and set the registers, update the registers maybe, or notify the registers. Okay, let's just start with these two and then we'll think about the rest. So first of all, we need a request. We need to actually put in a request. So let's see. Let's just define it here. Virtio. It's going to be request, right? Virtio blk requests. It is struct, so it's struct. And we can struct rec equal to, let's put here, and we'll put it in stack. Data, let's keep data as nothing. I think we can keep it as data as nothing. No, we'll think about it later. Let's just put the type. First of all, type is currently, it is Virtio blk. It's going to be out, so it's a write operation. And then we have, we'll have to use comma. And then we have reserved. Do we need anything for that? I think we can set reserved to 0. And then this is the key part, the sector number. Which sector do we want to write? And I guess in our example, we wanted to simply write into sectors 100. Whichever sector it is, we are just making an example case. Prepare a request to write into sector 100. Okay, what else? Must be 512 bytes aligned. Okay. Multiple of. Okay, then let's me just put. It simply said chain descriptors. But what does that mean? I was thinking because my chains are here. If you come to my which descriptor we have as next, and next is u 16. What the fuck? Then how the fuck will I know? Maybe it's just index? I don't know. Or maybe we just put all those things into the queue and we just chain them with next as the index. Index within the queue. I don't know. It's a mystery. Mystery yet to be solved or yet to be. It's awaiting for our mistake. Okay, so first of all, I need to know. I need to prepare a data buffer and pass it down there. Okay. Okay, I can prepare this buffer, it's fine. If I prepare this buffer, it can be just stack allocated. It doesn't have to be char data. It's 512. Just put 0 initialized it. And I can see this. Okay. And I put that into my data buffer. Data dot. But actually data is at least in my definition of data, it is it's what is it? Char of char what? Pointed to array of arrays, yeah. It's 5 arrays and 5 arrays within it. Or maybe it simply has to be wait. Let's go back to our should I pass data as pointed to array of array or was the data is expecting here? What the fuck? Allocate header data and separately set up 3 descriptors in the queue, chain them using. I freaking have no fucking clue what you mean. Give me an example with ASCII to picture. Okay, so we have the virtual descriptor. Okay, so let's say the 0th index points to the request header. What? Request is this? Oh, within the descriptor table, I fill in descriptor. So I just fill in like this. I don't fill in this information. I fill up this information with the starting address as maybe pointed to a request. And length. And I also set that next chain to next. Next is 1. And then I create a new descriptor as a new struct for this, and I point to a different address, and this will be a data buffer of length, and then I say what the fuck, it was never specified here. And we have a new, so entire memory layer will look like we have a header of type this, reserved is 0 and sector is 0, and then we have a new chain that simply has data buffer, and then we have another that has this. But then what's the point of the request struct having the data fields? Because as I understand, this structure also has this field. So what's the point? Like now, why can't they just simply have removed these two and have it like this, and have a different structure that's going to hold this information? It's not meant to be used as a single contiguous struct in memory. Instead serves as a logical representation of the request layouts. Okay. 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 But only after I saw this ASCII, I got an understanding of how we only use this, because our descriptor queue only accepts this. Within that, it has the address. So we allocate this in our end, and we just pass this address here, and we also pass the length and the flags, and we also pass next. And then we also make sure that the next time we allocate the same thing, we pass in a different thing, which is the data buffer. Oh, this is just amazing. I'm impressed by this design. Initially when I thought about it, I know that descriptors are chained, but then I thought actually descriptors are chained to get this information for some reason, but I was still gonna put this request directly into that queue. That's how I thought. So the idea is that we are only going to put descriptors into the queue, but within the descriptor we have the address, so we can pass in anything there, And technically the other person should be able to deserialize it into some structure. Interesting. But one more question is that how will which queue know that we are only passing proper request tract in the address or data or status? What if we pass some other address there? What will happen? Will it be validated? Okay, so it is simply going to read it anyway. But it checks for these information, but still it's going to read it anyway. Okay. So isn't that more like type confusion bug in V8? And so in V8, if a code assumes to read some other structure, but we can actually pass some other structure. Yeah, we assume some other type is going to be there, and we read some other type, and can lead to corruption. But technically, here if we can pass anything and it is still trying to read the queue length and next pointers from it, so it's actually reading something else, but it has some validation. So it will be a protocol misuse, not a type confusion. So yeah, we agreed that we are gonna only pass this, and if we pass something else, it's our fault. Yeah, makes sense. So I need this ASCII art. This is the perfect explanation that we can find out there of what we want to do. And where is it? Let's keep this art here. So this is what we want to do. We want to pass in multiple descriptors and we chain them together, and we pass the address of those requests properly, so that the other person, the other end can actually read it. Yeah, makes sense. Nothing special here. All we have to do is that we have to prepare 3 descriptors and requests, and we pass the request address here, and we pass this flag and the value. Okay, let's take these values and let's find them here. So we know the code for those. Oh, they have actually given the entire rich queue. Okay, let's just put that. We only need right and next. I think that should be enough. Let's define those two. And ESCF right, and it's 2. Separate this. C F next, which is 1. What else do we need? We have all of this stuff. Okay, now we can prepare 3 requests, I guess. Prepare these descriptors first of all. And one more thing, is this address virtual? Well, let's just confirm that. Those address should be virtual or physical. Because we are actually connecting it to a different thing. Must be physical. So we actually have to convert it into physical, and only then we can share it, because the other person is a completely different process and they won't have the pages. Let's just write the to do then. To do create the request with type and reserved and sector. Get the physical address of the request. Create descriptor with this address and chain as next. Create the data with some value. Get the physical address of buffer. Create a disk with this address and chain this next and right flag. Okay. We need physical addresses. Okay, I have one more question. So when we prepare this descriptor and we pass the descriptor's address into, so when I prepare a descriptor, it will be in my virtual range. Should I also get the physical address of descriptor? Oh yeah, I guess I already know about this, because even if I get this descriptor, I actually have to write the physical address of this descriptor into that register. Because what you mean by updating the what is that, the descriptor queue is just, descriptor queue is actually a what is this here, it's just two registers. We convert the virtual into physical, and we write the upper half and the lower half here. No. Yes. And we have already did that. We have already done that. Wait, no, I have another question. So already created a descriptor queue of size n and store the upper and lower half of the physical address into the registers. So now how do I put the new descriptor into the queue? I write the full bytes into the queue start and increment my physical address locally and write the next descriptor, because currently the queue is just the starting address, that is physical. I don't know if that question even makes sense, because what I have is that here, if you come here, I simply write, I have already allocated space for these virtual descriptor and this, and I have, let's say, queue of 5, so I have virtual descriptor into 5. You can see it here. Let's see, we have like kmalloc, and we just allocated that descriptor size. So what exactly do we mean by I think we simply have to, because I have allocated it here. Here I have allocated it as virtual descriptor, and I have a starting address. So I just keep on allocating So the descriptor array location should have a range of descriptor size into n. So that's the thing. So I have descriptor here, and I'm only allocating once, so probably I have to allocate it here like this, size into n, and n, let's consider n as 12, and avail ring will also be the same thing. I'll have to create 12 and into 12. So now that I have contiguous blocks of these records, the first descriptor will have my first request, and then I have to increment the address and write the next descriptor in my side. In the other end, the Virtio is going to probably have some sort of algorithm to iterate over it and find it, but in my case I'll have to update the pointer myself and write to the next descriptors. I think so, yeah. Yeah, without that, I guess that's the final question I needed to ask. Other than that, everything else is almost clear. Let's just write it. So we update the we increment the descriptor base address plus bytes used to go to next descriptor and write the info. All descriptor static size. To put the descriptor index into starting index into avail ring, and then notify the register. Okay, I think I have enough information. I should be able to do it. Okay, I guess today we managed to, in general, figure out how we can actually prepare the request, and we also managed to write back the features, because we did not do that last time. We wrote back the features, so the features are enabled. Now what's left is to actually prepare the request, and we also learned how the descriptor tables are actually in the memory. So yeah, and this is how the whole thing has to go. Yeah, we'll prepare that next time. I guess it's enough of theory for today. Thank you guys. Have a good day then. Bye bye.